Hey guys, so today we're going to do Unit 5, Lesson 8, and look at some exponential situations as functions. So this first example, we need to review what a function is. So we have accumulated rainfall in Las Vegas, Nevada, and we need to decide if the accumulated amount of rainfall is a function of time. So what's a function? A function is something where each input has exactly one output. So we need to look at the data shown in the graph, and it's saying the accumulated amount of rainfall is a function of the time. So we have y is a function of x here. So time is on our x-axis. And so the way that it is shown, if I draw a vertical line, this graph would pass the vertical line test at any given point. It's only going to touch the vertical line once. So this is a function because each number of days between 0 and 60, there's one specific amount of rainfall at that time. So there's only one value for each amount of time that we're shown. So then if we switch that, is time a function of accumulated rainfall? So now we need to know if time is a function of the accumulated rainfall. So if we take this graph and we flip it, and you're looking at it the other way, then we would have multiple outputs for 0 inches of rain. So 0 inches of rain right here is going to give you values all the way to 10, 1, 2, 3, 4, 5, all the way. Also, we have another line here that is the same. So the rain wasn't falling, there was no rainfall, so it's going to accumulate 0. So our answer would be no, there is no rainfall for the first 10 days, which would mean the input or amount of rainfall of 0 inches, there would be multiple times as the output because we would have the first day, the second day, the 9th day, all the way until the 10th day there. And the same thing would happen at about 9/10 of an inch of rain. So it would fail the vertical line test. All right, so here we have an inquisitive person here. Claire, she noticed a piece of mold on a slice of bread, and she decided to measure it and then track its progress each day. So the first day she noticed the mold, there was 1 square millimeter of mold. Okay, so that's important information we need to know. She left the bread alone to see how the mold would grow, and the next day the area covered by the mold had doubled, and then it doubled again after that. So it's going to continue to double. If it continues to double, how many square millimeters of mold will cover on the 4th day? So we know it's doubling. We had 1. If we double that, we get 2. Double it again, you get 4. Double that again, you get 8. And then double it once more, you get 16. Or 2 times 2 times 2 times 2 is 16. So we would have 16 square millimeters of mold. All right. Now we need to look at this and be able to make a table of values, an equation, and a graph. And so to make our table of values, we already have the initial value, 0. Okay, so our initial value is 0. And then we would just number them. Let me move that. Okay, so our table would look something like this. So we need the first 5 days that we have after we saw the mold. So on the first day was 0. The initial day, there was 1 square millimeter. Then it doubled to 2, doubled again and got 4, doubled again and got 8, double it again, you get 16, or we could just take 2 and raise it to that power. Okay. So our equation here, we're using our initial value, and our initial value is that 1 square millimeter that we talked about up top. And then the other part of your equation that you need is your growth factor. So it's always what it's increasing by or decreasing by that is going to be left. And so for this example, it would be 1 square millimeter for the initial value, and then it's doubling, so we would multiply that by 2 and raise it to the power of d, or the number of days that we're looking at. And then your graph, in lessons 6 and 7, we talked about how our x and y axes need to be set intervals that match the data. And so in lesson 7, we talked about windows that were too large, and so we couldn't see any of the data or what it was because they all looked the same. And then we looked at windows that were too small where we couldn't see enough of the data. And so we need to make sure that our windows show the data. So for this one, our x-axis needs to go 0 to 5 or 0 to 10. You can go out that far. And then our y-axis, we should have intervals that would get us past 32. And so for my graph, I continued it on, and we went all the way out to 7 days to see a whole week. And so I went by tens. And so the data is still spread out nicely, and so that you can see that. But you need to make sure that your intervals are equal when you're graphing. And then we need to decide how the relationship would look in our function sentence. And so our independent and dependent variables are key here. So whatever is on your x-axis is your independent variable, and that is time. And our dependent variable is the area in square millimeters. So our sentence would be the area covered by mold is a function of the number of days that have passed. So that means that at any given time since the mold was spotted, there is a certain area of bread that is covered in mold. All right, so let's look at 3 examples we've looked at in previous lessons. So in a biology lab, a population of 50 bacteria reproduce by splitting. Every hour on the hour, each bacterium splits into 2 bacteria. So we need to write the function sentence. So we need to decide what our independent and dependent variables are. And so time is almost always your independent variable. So for this one, it would be the population of bacteria, or the number of bacteria, is a function of the time passed in hours. Okay, so our independent variable here is time in hours, or number of hours, and your dependent variable is the number of bacteria. So then we can write the equation to represent this. We need to know what our initial value is. Well, it tells us that the population was 50 bacteria, and then it splits into 2. So that becomes our growth factor. So in function notation, we switch out that y for f of x. And in this case, we're going to use t for time. So we have f of t, or our input, is equal to 50, which is the initial value, times 2, the growth factor, to the power of t. All right. Every year after a new car is purchased, it loses 1/3 of its value. Let's say the new car costs $18,000. So for this one, we have years since the car was purchased, and we have the value of the car. So for this to be a function, the value of the car would be a function of the number of years since it was purchased. So our initial independent variable here is the number of years since the purchase of the car, and the dependent variable is the value of the car in dollars. Okay. To write our equation, we need to know what the initial value of the car is. Well, we paid $18,000 for it. And then it tells us that we lost 1/3 of its value every year. So if we're losing 1/3, we need to use the value that will be remaining in our equation. So we would take 1 minus 1/3, and that would give you 2/3. So in our equation, we would use 2/3. So we'll have f of t equals 18,000 times 2/3 to the power of t. All right, and our last example that we're going to look at is the algae bloom that we looked at in lesson 7, I believe. And so the area covered by the algae here is 240 square yards, and each day since the treatment began, 1/3 of the previous day's area remains covered. So time t is measured in days. So here, if we're talking about this algae bloom, then it would be the area covered by the algae. So what's changing is a function of the number of days since the treatment. So here, if we're identifying our independent and dependent variables, our independent variable is time, the number of days since the treatment, and the dependent variable is the area covered by algae. So it is in square yards. And so to write our equation, we would look to see what our initial value is. So our initial value is 240 square yards, and then it tells us that it's got 1/3 of the area remaining. So instead of having to take that away from 1, we already know that that's what's left. So we can use that in our equation. So f of t equals 240 times 1/3 to the power of t. So the important things to remember here are that you need your initial value times your growth factor. And your growth factor could be increasing, so it would be greater than 1, or it could be decreasing and be less than 1. But if it's less than 1, we want to make sure that we're multiplying by the amount that is remaining and not the amount that we're taking away.